Hello, this is Chuck Ridgway. Welcome to another Tuesday live stream. Here's our topic for today: performing sequential stepper moves with Horner OCS. Now, this is another topic that was requested by one of you, our viewers, which is wonderful. I love doing that. I get a chance to dive deeper into a topic at your request and hopefully create some content that everybody can utilize, not just those who requested it. Okay, so today I am fully live and we are standing by to answer your questions live. Just go ahead and give us those in the chat section. And as always, if you're watching on replay, give us your questions in the comment section. In either case, we'll get them answered right away. All right, let's take a look at our topic. Performing sequential stepper moves with Horner OCS. Here's how we've broken down the topic for today. We are going to talk a little bit about what we have covered in previous videos so you can see what's available to you to watch. And there is some good stuff out there. We're going to do a quick review of step and direction control, which is really the heart of performing stepper moves. We're going to talk about commanding a single move, and then we're going to get right into our topic, and that is using a user-defined function block, or at least that's the way we're going to implement the topic, by utilizing a user-defined function block to execute a whole series of moves. So we're going to create that UDFB for executing a single move, and then we're going to string them together using a couple different techniques to execute a sequence of moves. And throughout the whole process, we're going to do plenty of demonstrations. All right, let's get started. Now, about a year ago, we came out with a video called Integrating Stepper Motors with the Horner OCS, and I would definitely recommend, if you have not seen it already, go back and check it out. In that video, we went through what is a stepper motor, what are the advantages and disadvantages of steppers. We compared them with servos. We spent quite a bit of time on the trapezoidal move profile. We talked about using step and direction control, which of course we're going to revisit today, and we did a hands-on demo. So if you haven't had a chance to check out Integrating Stepper Motors with the Horner OCS, I would highly recommend that you do so soon. But it's not a prerequisite for today. Let's do a quick review of step and direction control. So stepper motors. Stepper motors are positioning motors that have several advantages. First of all, they have a fairly low cost. They have good performance when used open loop, which was how they're usually used. It's not very common for a stepper to be reliant on an encoder, or a stepper application to be reliant on an encoder for its operation. It can be used open loop very effectively. And part of the reason it can be is because it has good low speed torque. It also has good holding torque. So those are all advantages of stepper motors that make them popular even today. Now, traditionally, stepper motors have been controlled with step and direction signals. Now, today, of course, you can control a stepper motor over a network, maybe with CAN Open or with Modbus TCP. But step and direction is the traditional way of controlling a stepper motor, and that's what we're going to include today in our demonstrations. Now, with step and direction, you have an indexer component, and the OCS can act as a stepper indexer. And that indexer component sends a DC pulse train where each pulse represents a position increment. For instance, every pulse could tell the motor to rotate 1/400th of a revolution, for instance. Now, the distance that the pulse represents is going to vary by motor, vary by drive, but that's precisely how stepper motors work. And then the stepper drive converts that pulse train signal to motor current signals that will cause the motor rotor to be positioned. Nowadays, you can find all kinds of stepper motors that have drives built right in, and that's what I'm showing there on the screen. So when I talk about a stepper motor or a stepper drive, very often these days, they're integrated components. So now let's talk about commanding a single move. So how does an OCS actually command a single move? Well, let's talk about, first of all, that trapezoidal move profile, which I have shown in that diagram on the right. the OCS is going to be commanding a total distance to be traveled. If you want to think of the rotor turning as kind of a linear distance. So how far are we going to be telling that rotor to travel? And we're going to give it that distance in pulses. We're going to give it the number of acceleration pulses. In other words, how many pulses are we going to send it while we're accelerating? How many pulses are we going to send it while we're running at full speed? And how many pulses are we going to send it when we're decelerating? So that's how the total number of pulses that are sent from the OCS to the motor, that's how those are broken down. What about the speed or the frequency at which those pulses are sent out? Well, you have a starting velocity, which is the pulses per second, the number of pulses per second for the pulse train when motion begins. And then you have your running velocity, which is the maximum number of pulses per second that are achieved during the move. And effectively, we have 5 parameters shown on the left there. Those same 5 parameters I've just talked about are the ones that need to be specified in your program, in your Cscape program, so that the OCS's stepper function can execute the move. And all 5 of those parameters are mapped to real-world I/O points in the high-speed counter / high-speed output functionality in an XL series or XL prime OCS unit or in the X5. All right, so for instance, if you're using the 2-counter mode in an XL series unit, you have the ability to have up to 2 stepper motors that you drive, stepper number 1 and stepper number 2. Stepper number 1 has real-world I/O allocation as shown in the 3rd column of the chart, and stepper number 2 has the allocation as shown in the 4th column. And all of those parameters, starting velocity, running velocity, XL pulses, running pulses, and decel pulses, are all double integers in the application. Okay, so those are all double integer values. All right, so specifying how far to go and at what velocities, that's the first thing you need to do in your application. Next, you're going to have to control and monitor some digital bits that are also allocated to real-world I/O in order to cause the motion to begin, in order to trigger the motion. So for stepper number 1, you're looking at Q1. So you're going to want to map one of your variables, one of your Boolean variables, to Q1, which will effectively be the variable you manipulate to initiate motion. You're also going to want to monitor status coming back from the stepper functionality in the OCS, and that's coming back through 2 bits. For stepper number 1, it's I1617 and I1618. That first bit is a ready/done bit that tells you when the stepper function is ready to go. It also tells you when the stepper function has completed the move or is done. And then if for whatever reason you don't specify your move parameters properly, your velocities and your distances, then you could see the second bit turn on that you're monitoring, I1618 for stepper 1, and that's an error bit. And that basically tells you that the parameters you've set for your move are illegal, they won't work. Or it could mean that your move was interrupted. So maybe your start move bit that you turned on, let's say Q1, was turned off before the move was completed. You'd also get an error in that scenario as well. So again, we start out by setting our move velocities and our move distances through 5 double integer variables that are tied to AQs. And then we next manipulate Q1 as we're monitoring a couple of digital input bits to actually cause motion to occur and to complete motion. So let's take a look at this in spreadsheet form before we dive into the demo program that's available. So let's go through this process. We start by, as I just mentioned verbally, we set the move parameters, which are the AQs, for our distances and our velocities. And then we set the direction output. Now, I haven't talked about direction yet. I pretty much just talked about initiating the move through Q1. there's two steppers potentially built into the OCS, stepper number 1 and stepper number 2. The pulse output or the step output is available on Q1 and Q2 for those two stepper functions. Now, what about direction, you say? Well, you'll want to use a general purpose output, one of the other solid state outputs, to tell the motor which direction to turn, or tell the drive which direction to turn. When it's on, it may go clockwise. When it's off, it may go counterclockwise, or vice versa, depending on the motor and the drive combination. But because the direction doesn't change very often, you can use just one of the standard solid state outputs, like somewhere between Q3 and Q12, for instance, as your direction output. So we set our move parameters, we set the direction output because we know which direction we want to travel. We check to see if we're ready to move, if I1617 is on, for instance. If so, we can go ahead and trigger the move by turning on Q1. All right, and these, of course, are all the references that are tied to stepper number 1. After we've triggered Q1, we can check to see if I1617 turns off. If it does, it means we're moving. And if at any point in the process we see I1618 on, we know we've got an error. But if it remains off, then we're really just waiting for I1617 to turn back on again. Then we know that our move is complete. So that's the flowchart for commanding a single move. Now let's take a look at the standard demo program that is available that you can get from tech support or download from our website for making all this happen. So I'm going to go ahead and switch to Cscape now. And we are taking a look at this standard program. And you'll notice there's not a whole lot to it. Because really what the standard program does is it manipulates those digital bits. Now it assumes, I'll go ahead and scroll back up here, in the comment section it tells you what the appropriate real-world registers are that you need to set for all of your parameters, and which ones are that you need to monitor for status, and of course the bit that you need to set to initiate motion. And then it's very well commented, as you can see, and then there's really only 3 rungs going on here. Okay. Now in this demo program we had to use something to initiate a move, and we decided to use a function key, but it really could be anything. It could be a button on a touchscreen, whatever it happens to be. And when that move is initiated, we turn on our start move bit, which is tied directly to Q1 here, and we wait until the move ready done bit is off. When it is, we know a move is in progress, so we have an internal bit that says, hey, a move is in progress. And then while a move is in progress, when we see that same status bit turn back on again, it means we're done, and we can turn on another move complete bit, okay, which is another internal bit here, reset our move in progress internal status bit, and then reset our start move so we're ready for the next one. So that's really all there is to the simple demo program for executing a single move. But that's obviously only part of what we want to cover today. What we really want to cover is how can we execute multiple moves in sequence. So let's go back to our material and take a look at the next section. Before we actually go about the process of stringing together multiple moves, we're going to go ahead and create a user-defined function block that can effectively take that logic we just looked at, add a little bit more to it, and then give us a handy function block that we can call to execute a move. So what is it we want to create here? Well, in my UDFB that I'm creating, I want to be able to specify the total distance in steps or pulses that I want to move my motor. You know that, of course, we have to specify to the OCS. It needs to know the number of X cell pulses, the number of running pulses, and the number of D cell pulses, and those 3 added together will be the total distance we travel. But for my UDFB, for convenience purposes, I just want to provide the total distance that I'm traveling, and let it kind of handle the rest of it. Also, the UDFB should be waiting for a go signal to initiate the motion, and of course it should provide status telling us that the system has completed the move. Those are all the kind of things that I want to roll into, or some of the things that I want to roll into this user-defined function block. So here's the variables that I'm going to put together for my user-defined function block. On the input side, I'm going to have my go bit that initiates motion. I'm going to have an abort move bit as an input because I want to be able to kind of stop things midstream if necessary. So that's what that abort move will be used for. Of course, I've got to monitor move ready done. That's that bit that's tied to I1617 for stepper number 1. I also need to monitor my move error bit, which is coming from I1618 for stepper number 1. I'm going to have a destination position that I'm going to feed the block. And then I'm also going to need to reference the number of X cell pulses and the number of D cell pulses, because ultimately, of course, I am going to need to provide that information to the OCS so it can execute the move properly. So those are all the inputs to my user-defined function block. On the output side, of course, I have to reference my step output, which if I reference directly is Q1 for stepper number 1. I also have to reference my direction output. Which general purpose output am I using for direction? Could be Q3, Q4, Q5, whatever the case may be. Move complete is going to be, of course, an output of my stepper block. And then running pulses, the number of running pulses is going to be an output of my stepper block. That's because I'm taking on the input side destination position, determining whether that destination position is positive or negative, okay, because the way I've designed my UDFB, if the destination position is positive, I'm going to travel one direction. If it's negative, I'm going to travel the other direction. But the direction I travel just impacts my direction output bit. The number of pulses that I have for X cell, D cell, and running is always a positive number. So there's some manipulation that'll have to happen inside that user-defined function block for sure. A couple more things before we dive into the actual function block itself. First of all, keep in mind that user-defined function block variables, the input variable for the UDFB, the output variable from the UDFB, and the private variables for the UDFB, the ones that you create when you create the UDFB itself, those particular variables cannot be mapped to I/O points. Of course, the variables that are connected to them can be, but the internal variables for the UDFB cannot, so keep that in mind. Also, keep in mind that you have to execute care with UDFBs if you have multiple instances of the same UDFB that might be manipulating the same output bit. In other words, there's only one Q1 output for stepper 1, right? And that's the output that we use to create motion on that particular axis, if you want to think of it as an axis. So if we have multiple instances of UDFBs executing different moves, but they're all for axis number 1, then we have to be careful that those UDFB instances don't interfere with each other, at least in regards to the stepper output or output number 1. So that's something we'll have to look at as well, but I'll cover that in the content here. Now let's head back to Cscape and let's take a look at the user-defined function block that we created. So I'm going to go ahead and minimize this example program or this sample program, and I'm going to open up another Cscape file, and I'm going to dive right into the details for this UDFB that I've created. Now this UDFB is doing more than just executing the move by monitoring inputs and twiddling the output. It's actually doing a little more than that. So let's kind of go through what I'm doing here. The first thing I'm doing in the UDFB, and we're looking internally at the UDFB right now, is I am determining whether my move is in the positive direction or the negative direction. And I'm doing that by looking at the sign or checking to see if the destination position that's come in, is it greater than 0 or less than 0. If it's greater than 0, I'm going to turn on my direction output. If it's less than 0, I'm going to turn off my direction output. So this is controlling my direction based on the sign of the destination position. Now the next thing I have to do is, remember, I have inputs of destination position, which could be provided to me as either a positive or negative number. And then I also have provided to me the variables for the number of X cell pulses and the number of D cell pulses, which are always going to be positive. So as I need to calculate my number of running pulses, I need to make sure that I'm only dealing with a positive number from a destination position standpoint. So if my move is positive, all I have to do is take my destination position and subtract off my XL pulses and then my decel pulses, and that will give me the number of running pulses that the OCS needs to execute the move. No problem. However, if I'm moving in the negative direction, I'm going to first need to multiply my destination position by -1 before I subtract off XL and decel. Now, of course, a way I could have handled this in a single step would have been to have used the absolute move operator on the destination position and done it all in a single step. I did it a different way. That would have been equally as valid. Let's get to the portion of the UDFB logic where this is identical to what we had in our example. When our go bit turns on, we set our step output, we check to see when the move becomes in progress, and then we check to see when the move is complete. So that's identical logic to what was in the sample program. And then I added this little abort rung here so that if the abort input turns on, then I'm going to go ahead and clear my stepper output, and if necessary, just end the move early. Just have that there as an extra function of the UDFB. Now, real quick, I'm going to take a look at the variables that I have tied to this UDFB. I'll show those to you in detail. This is my program variable window. Here is my step rel move UDFB section, and here are all the variables that are tied to that UDFB. So you can see here my inputs, my outputs, and then I have one variable move in progress that's just an internal variable as far as the UDFB is concerned. Now you notice that none of these internal variables, ins, outs, or privates, none of these are memory mapped to Q1 or I1617 or AQ421 or any of those. That's because we're not allowed to directly memory map UDFB variables. Any memory mapping we do is going to be done on regular variables in the program. So elsewhere in this program, I have regular variables that are tied to Q1 and I1617 and AQ421, etc., because those variables that ultimately will be tied to the user-defined function block, those are the ones that are mapped to the OCS. So that's the UDFB I've created that's going to make it easier for me to string together multiple moves, and it's also a pretty convenient way, frankly, to execute a move in an OCS. Let's head back to our slides and continue on with our content. So now we're getting to the portion of our program where we talk about actually stringing together moves in a sequence, because it's very common in stepper applications. You want to move from point A to point B, and then to point C, and then back to point B, and then off to point D, and all those sorts of things. So that's a typical function of a stepper motor system, to do indexing to multiple stations in multiple directions with multiple positions. So I'm going to create an example here that basically allows up to 8 sequential moves, and we could easily do more, but I had to stop somewhere, so I set it up for 8 moves. Each move can be programmed for distance and direction. Each move can be programmed for a dwell time. So as we execute these moves sequentially, in between moves, we're going to be waiting a certain amount of time before we move to the next one. Now, in a real-world application, that may be exactly what you need to do. Move to a position, wait a certain amount of time, and move to another position. Or maybe you might have a scenario where you move to a position, wait a certain amount of time, and then wait for a certain input to turn on, like a sensor or something, before you move again. So there's all kinds of variations, but in this example, we're basically just allowing up to 8 moves, and with a dwell time at the end of each move. And we're going to utilize arrays for our move parameters, which just makes sense, right? So we're going to have step 0 through step 7, and with each step, there's going to be a destination position, and there's going to be a dwell time. So now let's head back to Cscape and close out our UDFB here, and let's go into some code I wrote for sequencing these moves together. Now, I wrote it 2 different ways, and both worked exactly the same, really, from the standpoint of the result of having up to 8 sequential moves. The first sequence I programmed, I used multiple instances of the stepper move UDFB. So every time I executed one of my up to 8 moves, every time I executed one of those, I called a different instance of the UDFB. So that's what I did. So let's take a look at this logic here. So this is going to be the longest, because for every step we're in, and we can have up to 8 steps, for every step we're in, we're going to have effectively 4 rungs. So we kick things off with a start push button. It could be kicked off anyway, but we're going to start the sequence as long as we don't have a current move error and as long as we're not already executing the sequence. When we do that, we turn on a flag that says, hey, we're executing the sequence, and we turn on another flag that says we're on our first step, which we're calling step 0, and then we also trigger a go bit for the first step. We execute this stepper move UDFB, the one I just reviewed with you. That go bit that we turned on here initiates the UDFB to execute. The destination position we use for the destination is sub-0 or index 0 from our destination position array. So that's something to be aware of. And then also, we've got the number of X cell pulses and D cell pulses that we're using for this move. Now in my example here, this example program, I use the same number of X cell pulses and D cell pulses for every move. You may do that differently in your application. And then on the output side of things, the output of this function block, of course, is we have an output that's going to ultimately be mapped to Q1. That's for our step to do the move, our pulse train. And then we have another output that ultimately is going to be mapped to our direction output to go either in a positive or negative direction. And then, of course, we have a move complete bit, etc. And then we had to calculate our number of running pulses. So effectively, we execute this move with this UDFB. Once the move is complete, we then execute our dwell, and the amount of time we dwell, time-wise, is going to be based on the dwell value in the array of dwell times. Once that is complete, then there's the next thing we have to do is to check and see, is this the last step or not? Now, I said there were 8 steps in this sequence, but it's up to 8 steps. So you can configure less than 8 by setting a parameter that says what the last step is. Maybe you've configured up to 8, but sometimes you only use 3, you only use 5, whatever the case may be. So it checks to see if the last step is configured as 0, because remember we're on step 0. If it is, we clear our step flag for this step, and we clear our sequence flag because we're done. Of course, if this is not the last step and our dwell is complete, then we clear the current step and we set the next step and the trigger for the next move. And then, as you can imagine, these same 4 rungs are needed for the next step, which is step 1, step 2, step 3, step 4, all the way to step 7, because remember it's step 0 through step 7. Now step 7 is a little different in that we don't need to test to see if step 7 is the last step, because we know if we've gotten this far, it's the last step. It's the highest one we're going to support. So it doesn't have to check to see if it's the last step. It knows it is. So after the dwell time's over with, it just immediately clears the step and the sequence. That's what I've done here for having 1 instance per move of the UDFB. Now, here's an important point I want to make. Don't miss this. And that is the outputs for step and direction for each UDFB are arrayed Boolean variables that are not themselves directly mapped to Q1 and Q3, which is in my case what I use for direction. Because of the fact there are multiple instances of these UDFBs, if the Q1 variable was mapped to each one of them, then they would conflict with each other. And the last UDFB in line would be the one that controlled the output. That's not what we want. Instead, I set up an array variable for step and direction for each of the UDFBs. And at the very end, I've got a rung for step and direction, which basically makes sure that, for instance, when I'm in step 2, that it's only the step output from step number 2, from my UDFB from step number 2, that's being used to determine the status or the state of my step output. This is needed, this logic is needed because of the fact that I have multiple instances of this UDFB and they're all potentially conflicting with each other when it comes to the step output. So I've given them individual step outputs and written this simple logic to control Q1 and Q3. So that's the, I guess you could say, the verbose way, or the lengthy way, logic-wise, instruction-wise. Let me actually show it to you executing now. So I'm going to switch to the overhead view, and here's the demo I've created. As I've stated on this first page here, of course, we're going to be able to execute up to 8 moves total, and we're going to be able to specify a dwell time at the end of each step. And then we're also going to have the ability to shorten the number of steps below 8 to some lesser number. Also important to know, for the stepper motor I'm using, which you can see here, of course, for the stepper motor I'm using, this particular stepper motor drive combination, it's an integrated unit, supports 1600 pulses per revolution. So for every 16 pulses I send it, it makes 1 full revolution. I've also decided, in looking at the information on this motor, that negative destination positions are going to move the motor clockwise, and positive destination positions are going to move it counterclockwise. Here's what my trapezoidal move profile looks like. And of course, I need to set up the number of accel pulses and decel pulses for each of my moves. Now, in my application, I've left them the same for every move. Okay, so the only thing that's going to change on every move is going to be the destination position, the total number of steps that's moved, as well, of course, as the direction, and as well as the dwell time. So I'm leaving fixed accel and decel. I'm also leaving fixed the starting and running velocities. Now, at 1600 pulses per revolution, this is basically 3 pulses per second is my starting velocity, and I guess 5 revolutions per second is my running velocity. 3 revolutions per second, 5 revolutions per second, just to give you an idea of what those numbers relate to. Now let's set up our sequence. So on this screen, I allow you to set for every step, and remember, we're going from step 0 to step 7. You can set your destination as well as your dwell time. And then positive numbers are, of course, going to be going counterclockwise in this case, and negative numbers are going to be going clockwise. And then I have the ability not only to set all my details for each step, but what my last step number is going to be. So if I want to run all 7 steps, I can use a 7 here. And then I can go to another screen I've created to kind of monitor what's happening. So let's go ahead and take a look at the execution of this. And I'm just going to hit the start button here. And our sequence is now active. You can see we're stepping through from step 0 to step 7. The little piece of tape I've got on the motor shaft there is just kind of flagging the initial position. All these distances are done with even numbers of revolutions, so you should see the flag end up at basically the same location every time. And you can also see that the dwell time is varying along with the distance traveled and the direction traveled. And we're just stepping right through from step 0 to step 7 because we went ahead and executed all 7. Now if I decide that I want to go ahead and make the last step number 3, then I can go back to this screen. My last step is number 3. I guess I could have changed it right there. Anyway, I can go ahead and hit start. And now I should go from step 0 to step 3 and then stop at that point because I'll be done with the sequence. And my sequence active indicator should turn off after the step 3 dwell occurs. So there's my distance for step 3 and my dwell, and then it turns off. So that's what the application looks like when I'm done executing it. And again, we'll post these programs at a location where they're accessible to you if you're interested in them. Now let's head back to Cscape. And now I want to show you a much more efficient version of this exact same logic that I wrote, which is another option. I'm sure some of you were looking at this logic, the real verbose version, and going, man, I could have done that way more efficiently than he did. And you're right. But I went ahead and configured or programmed another approach. And with this approach, instead of having 3 or 4 rungs per step, I basically configured it so it was just one sequence using one instance of the stepper move UDFB, and I used indirect moves and a rotate instruction to keep track of what step I was on. So how did this vary? Well, just like the other approach, it kicks off with a start push button. As long as there's no move error and we're not already executing the sequence, then we do one thing a little differently, and that is we set our current step to 0. So with this approach, I had to keep a numeric tally or keep track numerically of what step I was on. I'm starting off with step 0, of course. So if I'm going to start off executing the sequence, I'm going to set my current step to 0. And then I clear all of my step flags except for step 1. I set my execute sequence flag, and then away I go. Oh, and then off the end here, there's also I think there's yeah, there we go. It was hidden off the end here. I'll scoot it over a little further. There's also a start sequence one shot that is used to kick off a couple of indirect moves. What are these indirect moves for? Well, these are where we retrieve our destination position and our dwell times for the current move. And of course, since we're starting with step 0, then we're pulling from the destination position array. The index for the array that we're going to pull from is handled with the current step variable, which is currently set to 0 when we start our sequence off, and that it will index through as we go. And then whatever destination position is needed for the current step, that gets copied into a different variable. And then we do the same thing with the dwell time, exact same thing. We pull from our dwell array using the current step index and copy it into a different variable. And then we have a go move one shot that will be used to trigger our UDFB. Now, since this UDFB is the only instance of this UDFB we're needing, I went ahead and used the always on contact. Here's my go move bit that is used to trigger the move. Our destination position comes in along with accel pulses, decel pulses, etc., etc. Now in this case, because there was only one instance of the UDFB, I was able to directly map my Q1 output and my Q3 direction output to the function block. Since there's only one instance, there's no concern with any conflict there on the output coils, so away we go. So very similar to the last one in a lot of ways, but of course, having only one instance of the UDFB is a big difference. And then once we're done with this move for a given step, the move done bit is going to turn on, which is going to cause us to start our dwell timer. All right, when our dwell is done, then we effectively are going to check to see if this is the last step. Is the current step equal to the last step? Yes or no? If so, we're going to clear all of our step flags as well as our execute flag. However, if it's not the last step, which it usually isn't going to be for obviously if you've got more than one step, then of course you're going to have to move on to this logic. And that basically says, okay, if this isn't the last step, then I'm going to add one to my current step tally, and I'm going to execute this rotate function. What does this rotate function do? Well, it takes these 8 step flags and it puts a 1 into the next one. So if I start out with a 1 in step 0 and I execute a rotate by 1 position for those 8 bits, then my flag is going to be in step 1. My 1 is going to be in step 1. The next time I rotate, it'll be in step 2. The next time I rotate, it'll be in step 3, etc. All right, and then once I've rotated my step flag, I trigger another one shot, and we come all the way back up again, pull out our destination and dwell times, and run through the loop again. Basically, exact same result, but with more efficient code, maybe a little more challenging to follow, but not really that tricky. The things that are key to making it work are the indirect move functions for pulling only the data you need out of an array. And the other key is probably this, although there's other ways you could do it, but I thought this rotate, this multi-rotate function was also a pretty good way of executing the step flags. So that pretty much wraps up what I wanted to cover today with our program. So just to look back, we created a user-defined function block to execute stepper moves. Of course, these are all relative moves, not absolute moves. It could be done for absolute as well. There'd just be a little more code required. We created sequencing logic to use multiple instances of a UDFB in order to execute a whole sequence of moves. And then lastly, we created a more efficient alternative approach using a single instance of the UDFB to accomplish the same thing. So I hope that you got some good out of today's show. Even if you're not necessarily going to be executing stepper moves anytime soon, hopefully you saw a good creative way of taking some logic and turning it into a UDFB, and then a couple different approaches to executing a sequence when part of the sequence is executing a user-defined function block. A couple more things I'd like to cover real quick. Don't hesitate to subscribe to our channel if you haven't done so already. Of course, it doesn't cost anything. And if you choose notifications, you'll be notified every time we go live or every time we post a new video. Also, I want to mention that we're here every Tuesday at 2 o'clock. And even if I'm not fully live, we'll be streaming a pre-recorded video live 2 o'clock on Tuesdays, and there'll be somebody standing by to answer your questions. And of course, as always, if you're ever watching one of our YouTube videos on a replay, you can always give us your questions in the comment section, whereas you put it in the chat section if you're watching it live. Next week, we think we've got a good show for you, and that is we're going to go through using Modbus TCP for OCS to OCS communication. So we've talked in the past about the advantages of using Ethernet global data for OCS to OCS communication, and there are many. However, there are still some instances where it makes more sense to use Modbus TCP, and we're going to review what those instances are, and we're going to show you how just dirt simple it is to set that up. So, this is Chuck Ridgway signing off. I want to thank you for joining us for this Tuesday's program. I look forward to seeing you next Tuesday, and everybody go out and do some good today. Take care.